Welcome to the satellite communication course. Now next is about numerical we need to see here. That is GSAT-12 satellite is placed in the geostationary orbit at 83 degree east. That is about a placement of a satellite in a given orbit. That is location of a satellite. And Earth station is situated at a longitude of 77.2 degree east and a latitude of 28.6 degree north. That is about the location of the Earth. Find find the central angle. Find the central angle. Find the central angle. Find the central angle for this Earth station. Now the location of satellite orbit that station geostationary satellite that orbit is given, and then longitude and a latitude is given. So we can consider that a longitude and a latitude, and that using that we can find out the central angle. That central angle is nothing but gamma here, that is to be obtained, and that central angle is nothing but what, a cos of gamma. Okay, that central angle is nothing but a cos of a gamma. But before that, we should know that a longitude of the that Earth station and a longitude of the satellite. So longitude of a Earth station, that is about lambda a, is equal to what, 77.2 degree east. And because here that longitude is given in terms of east direction, so even here the satellite pushing the about east direction. So that is nothing but a longitude again. So that is nothing but what, a longitude of satellite, or we can say that's about a sub satellite point is equal to, we can say that is about lambda s is equal to 83 degree east. Yeah. So from that we can find out the difference of this longitude. That is the difference of a longitude from the Earth station to the sub satellite point. Okay, from the Earth station to the sub satellite point. That is nothing but what, lambda e. Say that lambda s here. So some people they have mentioned phi e phi s. Okay, likewise. So we have used this notation here. So we can find out what will be the delta lambda. So 83 we can consider that. Sorry, this one is about lambda s by lambda e. So 83 minus 77.2, that is nothing but a delta lambda. Okay, that is nothing but a delta lambda. Now our aim is about to find out the central angle here. So to find out the central angle, the equation for this central angle is what, a cos of gamma. I'll write here cos of gamma is equal to cos of whichever the latitude of this satellite is given. That latitude is nothing but what, we can say that 28 point some 28.6 something. Okay, so that is nothing but what, a cos of phi e. Okay, that is about a cos of phi into what we can calculate that whatever the difference we are getting, and that is nothing but a cos of delta lambda. Okay, cos of phi minus cos of a delta lambda. Now you can put that a cos of phi nothing but what 28.6 degree here into cos of delta lambda. Okay, that delta lambda, if you solve it, you'll get that delta lambda is about a 5.8 degree, means cos of 5.8 here. So we'll get that cos of a gamma term, and that cos of a gamma term after solving it will be 0.8736, means that is nothing but a cos of a gamma. And then we have to find out what will be the central angle gamma here. That is equal to a cos of inverse 0.8378736, and after solving we'll get that 29.1 degree here. That is about the central angle. Okay, so that's called as a central angle. So generally we can consider that earth here and a position. Okay, so position of a satellite. Now just we can calculate. So from that earth station to the sub-satellite point, and that is nothing but your delta lambda here. So we can find out what will be the location or sub-satellite point here from that particular longitude one. Next one, an earth station has the latitude of 23.023 degree north and a longitude 72.51 degree east. Okay, you can have an earth station has the latitude of what 23.0 and 72.51 east here. Find the slant range. Find the slant range from this earth station, to a geostationary satellite, to a geostationary satellite located at the longitude of 754 degree east. Now this term is given. Our aim is about to find out the slant range, and for the slant range we have to consider that what is the position of a satellite. So generally we consider that a slant range, so we need to consider that a sub satellite point, and then we have to consider that earth here, that the earth station, and from this to this. Okay, from this to this, and we take a projection of this here about 90 degree, and that becomes your slant range. Okay, so this distance is different. This distance is different. From the earth station to this, that is nothing but a slant range there. So our aim is about to calculate that a slant range. So to calculate the slant range, that R is equal to what? That is about RS 1 plus RE by RS minus, that's square, minus twice of RE by RS cos of gamma raised to 1 by 2. Re, R is equal to what? Rs plus Rs into 1 plus Re by Rs minus twice of Re by Rs. Okay, minus twice of Re by Rs into cos of gamma, that is central angle, raised to 1 by 2. This is under root of this. So what do you mean by this value of this Re and Rs? And that Re is nothing but what? Earth radius. This one is about the earth radius here. So similarly, this one is nothing but the earth radius. But from this to this is about a sub-satellite point, and here is about your satellite. So from this to this is nothing but the altitude h. So our aim is about to find the distance from the what? The center to this, and that is nothing but your RS. Okay, or generally somewhere we have mentioned that R here only. Okay, so that is about a radius of a geostationary orbit. That is a RS. That is from the center of the Earth. Radius of the geostationary satellite from the center of the Earth. So we need to find out that term slant range. So we should know that what will be this RS there. So Earth radius we know that. Okay, we know that what will be the Earth radius, and then that geostationary satellite is about the altitude about 35,786. Generally, we say that RS is equal to what? RE plus H. So RE is equal to Earth radius. That is about 6378 plus altitude is about 35,786 kilometers. So we'll get that RS. Now here the term RE and RS, we know that. This term, we know that. Now our aim is about to find out a cos of gamma. So this one is nothing but what? The cos of this central angle, cos of central angle is equal to what? Cos of phi into cos of delta lambda. That cos of phi, that is about what? A 23.023. That is 23.023. That is towards north. Then cos of delta lambda, this cos of delta lambda is nothing but the difference between this longitude. Okay, from the satellite to the earth. So that is about 74 minus 72. So that is nothing but what? Delta lambda is nothing but what? 74 degree minus 72.51 degree. Okay, that is about, you can say, it's about a difference. That is nothing but a delta lambda term. And this is nothing but your phi. So after solving, we'll get that cos of gamma term. Okay, this cos of gamma we are getting, that is in terms of what? A 0.91998. Now this term, if you put this or in the equation of R, RS, RE and all these equations, after solving this, you'll get that R, that is about a slant range, that will be is equal to what? 31399.5 kilometer. Okay, that is about a slant range. So we'll get that slant range from this equation. Even using the same, we can find out what will be the azimuth there. Okay, using this. This is about the slant range we obtain. So similarly, we can find out the azimuth also for the same numerical. To find out the azimuth, so that is about the equation for this azimuth is equal to what? A sine of Az, sine of Az is equal to what? Sine of delta lambda divided by sine of. So sine of Az is nothing but the azimuth. Sine of delta lambda is nothing but what? A difference in the delta lambda is equal to what? This one. That is about a 74. 74 minus 72.51. That is about delta lambda. And this gamma, that is about central angle, sine of gamma. So cos of gamma, already we know that central angle. So we can calculate that gamma is equal to what? Cos inverse of 0.91998. You'll get the gamma here. And that gamma is equal to what? Is equal to, if you solve it, you get that 23.077 degree. That is about the cos of gamma. Put that here. So we'll get that sine of AZ is equal to sine of 74.72 something. That is nothing but a 1.49 degree. So here 1.49 divided by sine of 23.077. So if you put all this term here, so you will get that sine of AZ is equal to 0.00663. After that, you get that AZ is equal to sine inverse of this one value. You will get that AZ is equal to 3.8. That is nothing but the azimuth here. So you can put all the values, you will get directly the azimuth. So if we consider that this azimuth, so same that term, from same term we can find out the elevation also. To find the elevation, so cos of theta is equal to Re plus H 1 minus cos square phi e cos square delta lambda pi H square plus price of Re plus H 1 minus cos of phi e cos of delta lambda bracket raised to 1 by 2. So here we need to find out the theta, that is about the elevation, that is elevation angle of the earth. So this we know that Re we know that is about the height, that is about altitude we know that 35 something. So this term we are getting. Now cos of phi, that is about a phi, we have we, that is nothing but what? A 23.0239, that is degree north. Cos of delta lambda, that is about a difference in a longitude from the satellite to the earth there. And if you put all these values here, so you'll get that cos of theta term. That cos of theta is equal to 0.4553. So you'll get that theta is equal to 62.92 degree. That is nothing but the elevation angle of the earth station. Okay, that is nothing but the elevation angle of the earth station. So these are about, we can consider to find out the elevation of the earth. Okay, so then we can use this to find out that what will be the azimuth, then what will be the slant range of the earth. Next one, find the tilt angle, find the tilt angle for a geostationary satellite, for a geostationary satellite with respect to, okay, with respect to an earth. Okay, so instead of that, to an earth station with, okay, an elevation angle of 5 degree, elevation angle of a 5 degree. So for this we need to calculate that, find the tilt angle. and that tilt angle, it is nothing but the angle between, or you can say that it can be measured from this satellite, whatever they where we have to say that a line joining the satellite and the Earth station at a sub-satellite point. Okay, so line joining the satellite. Okay, so line joining the satellite and then Earth station and sub-satellite point. That is nothing but a tilt angle. And that tilt angle is nothing but what T is equal to what sine inverse of Re by H R, that is about slant range, into sine of gamma. Okay, so we can calculate that. So for the given particular orbit, or you can say that a particular satellite, and we can calculate that a tilt angle there. So we can use the earlier values, okay, and we can calculate that a tilt angle. We can put all the value here. You will get the tilt angle. That is about